Welcome to G Fun Facts Online. Today, we're venturing into the deepest realms of mathematics to explore a concept so vast and profound, it's been called a grand unified theory for the entire field. It's a story of hidden connections, a mathematical Rosetta Stone that translates between worlds that were once thought to be completely alien to each other. This is the story of the Langlands Program. Imagine mathematics not as a single subject, but as a continent with many different countries. In one country, you have number theory, the study of whole numbers and primes. In another, you have harmonic analysis, the study of waves and vibrations. And in yet another, algebraic geometry, the study of abstract shapes. For centuries, these countries spoke different languages and used different tools. Then, in 1967, a 30-year-old mathematician named Robert Langlands sent a 17-page letter to the eminent André Weil. He began with incredible modesty, writing, "If you are willing to read this as pure speculation, I would appreciate that. If not, I am sure you have a wastebasket handy." What that letter contained was anything but trash. It was a revolutionary proposal, suggesting deep, secret tunnels connecting these different countries of mathematics. Langlands conjectured that the fundamental objects of number theory, called Galois groups, were intimately related to the fundamental objects of harmonic analysis, called automorphic forms. This set of ideas, now known as the Langlands conjectures, created a dictionary, a way to translate problems from one field into the other. A problem that seemed impossible in the language of number theory could now be translated into the language of analysis, where it might suddenly become solvable. For this visionary work, Robert Langlands was awarded the prestigious Abel Prize in 2018. But what are these strange-sounding mathematical objects? Let's break down the three pillars of the Langlands program: Galois groups, automorphic forms, and the bridge that connects them, L functions. First, Galois groups. Think of these as the symmetries of numbers. Consider a simple equation like x squared minus 2 equals 0. The solutions, or roots, are the positive and negative square roots of 2. You can swap these two roots, plus square root of 2 and minus square root of 2, and any true mathematical statement about them remains true. For example, the fact that the root squared equals 2 is true for both. A Galois group is the collection of all such possible symmetry operations for the roots of an equation. These groups capture the essential complexity of number systems. The ultimate goal for number theorists is to understand what's called the absolute Galois group of the rational numbers, a monstrously complex object that holds the secrets to every possible polynomial equation. Think of it as the master key to all of number theory. Now, let's travel to a completely different world: automorphic forms. These are the harmonies of analysis. You're already familiar with simple periodic functions like sine and cosine waves, which repeat themselves over and over. Automorphic forms are a vast generalization of this idea. They are incredibly symmetric functions that live on more complicated geometric spaces. Just like a complex musical sound can be broken down into a combination of pure sine waves, a process called a Fourier series, a general function on one of these geometric spaces can be broken down into a sum of automorphic forms. They are the basic building blocks of harmony in this analytical world. A key example are modular forms, which were essential to proving Fermat's last theorem. So we have the symmetries of numbers on one side, and the harmonies of analysis on the other. How do we connect them? This is where the third pillar comes in: L functions. Think of L functions as the bridges between these two worlds. An L function is a special kind of function that can encode a huge amount of information. The most famous example is the Riemann zeta function, which holds deep secrets about the distribution of prime numbers. Here's the critical part: you can build L functions from both sides of the divide. From the number theory side, you can construct what's called an Artin L function using a Galois group. From the analysis side, you can construct a Langlands L function using an automorphic form. The central idea of the Langlands program, the core reciprocity conjecture, is breathtakingly simple to state. These two types of L functions are actually the same. For every Galois representation on the number theory side, there corresponds an automorphic form on the analysis side, and their L functions are identical. This isn't just a neat trick, it's a profound correspondence. It's the Rosetta Stone that allows for translation. An even more powerful idea within the program is called the principle of functoriality. It's a mechanism for transferring information. It suggests that if you understand the automorphic forms for one type of group, you should be able to make precise predictions about the automorphic forms for other, related groups. Functoriality is the engine driving much of the research today. If proven in its entirety, it would provide an incredibly powerful toolkit for generating new mathematical insights. So has this abstract web of conjectures actually achieved anything? The answer is a resounding yes. Its greatest triumph is a story many of us know. The proof of Fermat's last theorem. For 350 years, the problem stating that x to the n plus y to the n equals z to the n has no integer solutions for n greater than 2 stood as the Mount Everest of number theory. In 1994, Andrew Wiles, with help from Richard Taylor, finally conquered it. His strategy was pure Langlands. He didn't attack Fermat's theorem directly. Instead, he proved a special case of the Langlands program, known as the modularity theorem. This theorem states that every elliptic curve, an object from number theory, has a corresponding modular form, an object from analysis. Wiles showed that a hypothetical counterexample to Fermat's last theorem would create a very strange elliptic curve that could not possibly have a corresponding modular form. This would violate the modularity theorem, so the counterexample couldn't exist. The proof was a stunning demonstration of the program's power, using tools from analysis to solve a centuries-old problem about whole numbers. Another major success was the proof of the Sato-Tate conjecture. This conjecture describes the statistical behavior of points on elliptic curves over finite fields. Again, the proof was achieved by using the deep connections between number theory and automorphic forms provided by the Langlands program. But the story doesn't end there. The program is constantly expanding. One of the most exciting new branches is the Geometric Langlands Program. This arose when mathematicians realized that both sides of the correspondence could be rephrased in the language of geometry. This geometric perspective allows for the use of powerful new tools. And in a monumental achievement announced in July 2024, a team of mathematicians led by Dennis Gatesgory and Sam Raskin reported a proof of the Geometric Langlands conjecture for complex numbers. This is a landmark result, the culmination of decades of work, that is expected to energize the field for years to come. Perhaps the most surprising development of all has been the discovery of a deep connection between the Langlands program and theoretical physics. In 2006, physicists Anton Kapustin and Edward Witten discovered that the geometric Langlands correspondence is mathematically equivalent to a concept in quantum field theory called S-duality. S-duality relates two different physical theories, one at strong coupling and one at weak coupling, showing they are secretly the same. The fact that a deep physical symmetry is described by the exact same mathematics as the Langlands program was a revelation. It suggests a fundamental unity in the structure of our mathematical and physical reality. This connection is now a two-way street. Physicists use Langlands ideas to understand quantum theory, and mathematicians use physical intuition to make progress on the conjectures. Despite these incredible successes, the Langlands program is far from finished. The overarching functoriality conjecture remains unproven in its full generality. Its proof is one of the ultimate goals of modern mathematics. Research on the p-adic Langlands program, which uses a different number system crucial to number theory, is pushing new frontiers. And mathematicians are still working to understand the full implications of the recent proof in the geometric setting. From a speculative letter written over half a century ago, the Langlands program has grown into one of the most ambitious and far-reaching intellectual projects in history. It has unveiled a hidden unity weaving through the fabric of mathematics, connecting numbers to harmonies and algebra to geometry. More than a collection of theorems, it is a new way of thinking, a guide that points toward a deeper, more unified understanding of the mathematical universe. The grand tapestry is still being woven, and the Langlands program continues to provide the golden threads that tie it all together.